Hello, everyone, and welcome to Ingenious Talks Online, a new affordable breakthrough in visual effects technology. Thank you for joining us today. So my name is Laura Kilpatrick, and I'll be serving as the moderator for today's event. So first, we'll start with a few housekeeping items. So this is a Zoom webinar, which means that all attendee microphones and videos have been disabled. However, you do have the option to type a question by typing in the Q&A box on your screen. So while questions will be answered during the question and answer period, we do highly encourage you to type them as they come to mind. So you just type them into the box and you don't need to wait until the question and answer period. So you can also use the chat box on your screen to talk amongst each other. For the question and answer period, while we just want you to be mindful that there could be a high volume of questions, and we'll try to answer as many as possible. So today's event will be recorded and will be posted to Carleton's YouTube channel. And finally, at the conclusion of the webinar, a brief survey will appear on the screen. And if you do have the time right then and there, we would really appreciate your feedback. All answers are anonymous. So now I'm pleased to introduce to you our speaker, graduate student Leah Zhu. Leah is pursuing her PhD in information technology at Carleton University as part of the Faculty of Engineering and Design. She received her engineering degree from Beijing Normal University in 2018 and a master's in IT degree from Carleton University in 2020. Her research interests include the improvement of realistic 3D computer animation and computer machine vision applications. She's interested in solving problems in the industry with relevant and practical researches. During her master's study, her research focused on improving vision-based depth generation results with new stereo system and applying the system in the film post-production pipeline. Today, Leah will be speaking to you about a new breakthrough in affordable visual effects technology. Please help me in welcoming Leah.
Hello, everyone. Thank you for coming and joining us today. My name is Leah. And today I'm going to share the research that I've done during my master's study under the supervision of Professor Chris Jocelyn. So it is quite an interest-driven project. So there's so many funny stories behind it, but the very original motivation behind the research was my second year's master's studies course. So at that time, I did a directed study with my professor, and it was about visual effects industry, visual effects technologies. And that in that course, we are asked to understand and implement many visual effects technology that are used in current industry. So there's one technology that I try to implement and integrate it into my own project that was really annoying. So it is called rotoscoping, which is a concept we will talk about later. And so when it came to the time that my professor was discussing the topic for my master's thesis, he was like, do you want to do something to automate the rotoscoping process by using depth? I feel like, wow, yes, let's do this. So here it is. We designed a new multi-view stereo system for better qualities disparity sequence generation. And also in the research, we explored its potential application in video post-production. So we call this system Perceiver. Let's start from the idea of post-production. So post-production is a very long pipeline that consists of many techniques and technologies. The purpose of post-production is normally to composite special effects or visual effects that can hardly accomplished in a real-life scenario into a video or image that is filmed or shot in a real life scene. So there are many technologies included in post-production, such as rotoscoping, chroma keying, 2D and 3D tracking, 3D animation, and rendering. But one of the most annoying one is called rotoscoping. The idea of rotoscoping is to trace over objects' silhouette frame by frame and enable the capability to cut it out from the background so that we can insert whatever effects we want behind it. And according to our friends, who is also now working on a visual effects industry, a 1 minute rotoscoping might take a month for an outsourced company to finish to give a usable result. So yeah, it's very time consuming and tedious. Since rotoscoping is so annoying, there's another method that is used in current visual effects industry, which is called chroma key. So the idea is to film a target object against a green screen or blue screen so that the computer program will be able to extract this range of color from the background and replace it with a virtual background. So chroma key also has its own drawback, such as color spill, that if a light shade object is in the foreground, it can easily get reflected by the screen color. And when we are trying to extract that color from the view, then the foreground object will have some weird semi-transparent effects on it. So we will have to add into some manual adjustment. And also for chroma keying, it takes up a lot of time to do some preparation to set up the scene and lighting, because for a nice chroma keying result, we want soft shadow for most of the objects in the scene. And since our research proposed to use disparity or depth map to simplify this process, let's talk a little about disparity. The idea of disparity or depth map is to reflect an object's position in a scene by a kind of grayscale image, so that the objects closer to the camera have lighter shade and the objects further away are darker. There are many techniques that are existed and well researched to generate depth, such as time of flight. So it's a technology to use infrared light that travels between the target element and the sensor. And the distance is measured by the time that the infrared light travels between the object and the sensor. LiDAR, similar idea of time of flight, but using near infrared laser. So it wouldn't interfere with sunlight and can be used in an outdoor environment. Both of these technologies are very accurate and efficient within a distance. So the distance is also a constraint to them, that the objects closer to the sensor will have a nice resolution, but the objects further away will have much, much less resolution. And also there are methods such as structure light, which is another well-discussed method to acquire depth in academia. The idea is to project coded line pattern on 3D objects, so it can nicely reconstruct the 3D model of an object and accordingly it steps. But one limitation of structure light-based stereo is that it has to be used in an indoor environment. So correspondence stereo is another side of the story. The idea is to simulate human visual system that perceive a scene from two different perspectives with two cameras. And with the data acquired by this camera pair, is called stereo pair. In the stereo pair, we are able to find one feature point from one image, then search along an epipolar line to find another corresponding point in another image. And by knowing the pixel difference, the pixel distance between the correspondence points, we can then use some triangulation magic to get the distance between the camera and the target object. And by putting the calculated result into a grayscale image, we will have a depth map. Sounds like a very nice solution for generating depth because it's neither constrained by the environment, it's applicable in both indoor and outdoor environment, and it's also not that much constrained by the distance. However, the quality of correspondence stereo can be easily influenced by any discontinuities or ambiguities in the stereo pair. So let's take an example from the stereo pair here. As you can see, some part of the left view cannot be found in the right, and some part in the right cannot be found in the left. And these areas are called occluded area in the stereo matching process. And these are also the places that can easily generate errors and noises in the final disparity map. So the problems we are trying to solve in the research is first, how to generate disparity map with less noises and errors by reducing the occluded area, or say the ambiguity or discontinuity in the stereo pair. And second, how to use the disparities to simplify an object extraction process. Our proposed solution is to surround a main camera with 4 secondary cameras that each of them form a pair with the center camera. With these 5 cameras, we are able to acquire 5 video streams looking at the same scene, but from 5 various perspectives. And by doing correspondence matching pair by pair for them, we are able to generate 4 disparities. And by combining them together, we should be able to get a merged disparity. And if the object boundaries are well defined and noises are effectively reduced, we should be able to separate a scene into several different layers by using the depth of the object. So after a preliminary validation in the virtual environment, we quickly started our system design in a live action that is applicable for live action scenario. So in hardware part, we used 5 programmable cameras from Point Grey and synchronized their frame rate and many other camera parameters with GPIO cables. Also, we 3D modeled camera mount and 3D printed them out with our Makerspace 3D printer. So this is how they look at the end. The picture in the left is the very first version that the cameras can easily rotate and translate. So we designed another version for it, which is the picture in the right. We added a lens holder for the cameras so that we can minimize the relative rotation and translation among the camera. But wait, why we want to do that? Why we want to minimize the rotation among the cameras? This leads to another interesting topic in stereo vision, which is called image rectification. So as we mentioned in the previous section, the correspondence matching process search along the epipolar line to find the correspondence points. But that is by assuming that the 2 images are perfectly on the same image plane. They are coplanar. But that's not always the case in a real life scenario. The cameras always have some relative rotation or translation between each other, more or less. So this is where the image rectification comes in. So what image rectification does is to calculate a virtual common plane that we can reproject the actual image onto the virtual common plane, where we can easily apply the correspondence algorithm and find the corresponding points with less efforts. And some existing researchers have proved that with rectified stereo pair, we can generate much, much better disparities. And this is also one of the reasons behind the fact that why existing multi-view stereo method mostly arrange the camera like this on the same axis. However, our system arranged the camera on 2 different axes. That is because due to the constraint of epipolar geometry, it is almost impossible to rectify the cameras on 2 different axes. So that is why most of the multi-view stereo method arrange the camera on the same line. But when I get to know this point, I was already like in the middle of my thesis. So I did go through some very desperate time. And even though we didn't really want to rectify all the cameras together, we want to consider them pair by pair. Applying image rectification will give us 4 different versions of the rectified center image, because there's different relative rotation or deviation between different camera pairs. And if we use them to generate the disparities, the object's boundaries wouldn't align, which wouldn't allow us to merge them together. But after being stuck here for like a month, we finally figured out a way, which is simple and practical. So as we mentioned, the idea of image rectification is to rotate the original image plane to a certain amount, or say project it to a virtual common plane. That is by multiply it with a matrix, which is called homography, that stores the amount that the image needs to rotate. So it will be projected on the virtual common plane. But what if we keep a record of the homography and use the rectified image to generate the disparities regardless? Then we just divide the disparity with the original homography. We can restore the disparity to the original image plane where the object's boundary would align. So problem solved. And also this explained why we want to design the lens holder for the 5 cameras, because if we don't try to minimize the relative rotation among the cameras, the rectified result will be hugely distorted. And we will have to crop out a lot of important and usable information from the acquired data. Now, solved problem number 1 now to problem number 2. The only thing we need to worry about now is how to merge the 4 disparities and select appropriate depth value from them. So in the research, we took the occlusion map as a reference. Like we mentioned before, the occluded area are like a shadow on the wall. So by using one light, we might not be able to eliminate the shadow. But by using a lot of light, just like the shadowless lamp in a surgery, we can eliminate the shadows. And this is how our system works. So we just choose the depth value that are considered reliable based on the occlusion map and get rid of those that are considered unreliable. And also we introduced a threshold to filter the values, the potential incorrect value from the disparities. And then we will get a nice and clean disparity. So in the experiment part, we designed both virtual and live action environments to evaluate our method. In the virtual environment, we built 2 scenes that each of them have 6 versions. Yeah, 6 versions. So 3 for stereo generation, that the environment goes from ideal to realistic, and 3 for chroma keying, also from ideal to realistic. And for the live action environment, we also filmed both stereo version and chroma key version, so we can compare their matting accuracy later. So to display the results are displayed in quantitative and qualitative parts. in terms of depth accuracy, we compared our method with traditional one-pair stereo matching method. And it turns out that our method always have better depth accuracy than traditional one stereo pair method. And when the environment goes from ideal to realistic, our depth accuracy remains stable, while the traditional method accuracy goes down a lot. I think the video would be a better illustration. So as you can see, the traditional stereo, due to the limited information acquired, it has a lot of noises in the background and the occluded area. However, with our method, the accuracy of the depth remains stable, even though the environment goes from ideal to realistic. And it followed the same pattern in the live action scenario. So for the matting part, we compared our method with chroma keying. For chroma keying, we used Keylight 1.2, which is a very widely chroma keying tool. And you can find them from like software such as After Effects. And also it provides us a lot of parameters to adjust so that the chroma keying result can reach a very nice level after the adjustment. So we also include the adjusted and unadjusted version for the chroma keying. And by looking at the chart, it's not surprising to see that in the ideal and semi-realistic environment, our matting accuracy sometimes is even less than chroma keying, because, well, chroma keying is a technique that has been developed for decades. But when it comes to the realistic environment, even the adjusted chroma keying result is not as accurate as ours. And also, another noticeable factor is that the unadjusted chroma key result is always lower than ours accuracy, which means chroma key always needs some manual adjustment, while our method can get a decent output by running automatically. And by looking at the videos of the matting, it's not hard to notice that even though our method doesn't perform that well in the details, such as the moving field grass on the rock, but it looks pretty well within the objects because it's not influenced by color spell or the shadow. So in the live action scenario, it followed a similar pattern that for chroma keying, we always need to do some garbage matting to get rid of the area that is not covered by green screen. And also there's some shadows from the screen that needs us to do manual rotoscoping. But by using our depth sequences, we can just select arbitrary range of depths and mask it out. To further illustrate the advantage of our method, we also did a composition test for both of the environments. So in the virtual environment, we are trying to composite a sandstorm and fog effects into the rock scenes. So it's not hard to see that by using chroma key, we have to completely replace the background. And the color spill on the ground can create some like weird halo on the foreground. However, by using our disparity sequence, the effects are nicely composited into the scene that follows the physical rules in the real life scenario, that objects closer to us has less influenced from the effects, but objects further away have more effects on top of it. And similar idea in the live action scenario. Here we have a video for the composition test. So as you can see, by using the depth, we don't have to readjust the colors on the object, and it reflects the depth of the object very nicely when we are compositing the effect into the scene. Well, that's me holding a chair in the backyard. So yeah. And yeah, hopefully with our system and with some further improvement, actors and actresses wouldn't have to run into man-made sandstorm or fire or explosion, which are really dangerous. And also some nice buildings and objects we don't have to create digital double for them to reflect the depth of them. And also we came up with several applications, potential applicable areas for our research, such as machine vision, autopilot, augmented reality, where if we have the depth of the foreground character, it can sort of intersect with the virtual element. And also image processing. I believe most of you have this function in your phone that the cell phone can simulate the big aperture camera to defocus the background. But due to current depth generation limitation, some part of the objects can be weirdly blurred out. You never want to go to a beautiful attraction and take a nice picture, but end up with part of your hand or hair weirdly blurred out. So yeah, these are some nice applicable areas of our research. And in the future works, also it's the limitations in our previous research. And it's also something we are trying to improve in currently. So in the previous research, we didn't involve user study for like evaluating the result. But in the new iteration, we would like to invite some visual effects artists from the industry to examine I'm sorry, there's an echo over there. We will have a better overview of our results from the industrial perspective. And also we would like to add some more complex scenarios into the experiment stage. And also in the previous research, because we didn't compare our method with some other multi-view stereo method that arrange the cameras on the same axis, we should definitely do that in the new iteration. And also we believe that introducing some better color matching method between the stereo pair can give us a better output. So yeah, I guess that's all. Thank you for your careful listening. And if you come up with any suggestion or idea about our research, please feel free to contact me. Thank you.
Perfect. Thank you so much, Leah. Very
Thank you,
informative. Yeah, so now we're entering the question and answer period. So I do see that there are a few questions in the Q&A box that have been submitted. Feel free to submit a question if you haven't yet already. And we'll go through them, Leah. Okay?
Yeah.
Perfect. All right, first up. To what real-world applications will the depth accuracy improvement of this process give a cost benefit?
Well, like normally when we are in the film industry, we need to use like rotoscoping or chroma keying to replace the background or say extract the foreground. But by using our method, it's basically a grainless keying method. And so that we don't have to like ask the artist to spend so much time on rotoscoping the area that are not covered by green screen. And also it's not constrained by the environment because we don't even like really need the green screen anymore. So I believe it can kind of, well, if the technology is well developed and can reach the several accuracy, then it can cut off a lot of budget from the post-production pipeline. Yeah.
Perfect. Thank you. Next up, new smartphones have multiple coplanar cameras. Is your technique being used there? So we'll start with that.
Oh yeah, that's a very good question. So yeah, why not? We can definitely, so we can also translate this kind of method and technology into a lighter weight program. So it can be applied in the smartphone for sure. And also, but well, smartphone only have, I think, 2 or 3 cameras mostly for most of the smartphone in the market. And smartphone, their lenses have a lot of distortion because they have limited aperture size. So it's definitely not applicable in the film industry or a cinematographic quality, but it's definitely an interesting way to integrate such technology into smartphone to get the smartphone user a nice interactive with their like daily activities.
Great. And then a second part to this question. So also, do you see a future to this technique in self-driving cars?
Yeah, so that's a very good question. So in the beginning of the research, we really thought about the possibility to use this technology in such as autonomous car. But to be honest, I recently read about paper from NVIDIA's vice president, David Nister. So in his paper, he mentioned that for autonomous car or maybe machine vision, the emphasis of depth should be more on detectability instead of the beautiful edges on the objects. So I think we are like kind of using the similar solution, but on 2 different directions. For now, we are focusing on improving the image processing quality and also like the edges of the objects. But in future, we can definitely explore the possibility of apply such technology in autonomous car or say autopilot.
Great. So is this technology very useful in AI and or military applications?
AR or AI?
AI.
I think, to be honest, I think AI will help improving this technology. Like, so there's some method that use deep learning or machine learning to take a better advantage of the relationship among the frames. For now, our method is just to process the images frame by frame. But what if we can use like deep learning and machine learning to take a better advantage of the relationship among the frames, or maybe take a full use of the occluded area and occlusion map. I think that would give us an interesting result. And also, if such technology is applicable in machine vision, then well, AI will help us. Actually, artificial intelligence will help us to improve this technology. And there's what is the one other than AI that he mentioned?
It was military.
Oh, military. Haven't thought about that. But I think with accurate depth, maybe it can be used for, well, I really don't have much idea about it. Sorry.
No worries. Right. So what is the main difference between your prototype and other products like this on the market?
So to be honest, I don't see much prototype like this on the market. There might have some other depth-based keying method, but they need some a huge tracker wall. It works more like augmented reality to figure out the camera's path in the 3D environment instead of by using stereo vision to cut out a foreground objects. So I think for now, our system is still quite unique in the market.
Perfect. Have you considered adding signal processing to smooth out errors in the camera outputs? For example, a small computer like Raspberry Pi per camera could clean up pictures.
Oh, that's a very nice suggestion, to be honest. So yeah, definitely. Like if we can externally process or say rectify the image beforehand instead of gathering all the data together and put them into computer to be processed, that would be very nice. And also, like for the different cameras, they all have some color mismatch between each other. And if that can be put into an external processor to get clean up, that would definitely be helpful. That's a very nice suggestion, much appreciated.
Another question is, have you considered adding more cameras? Have you looked at better quality cameras?
To be honest, we did. So adding more camera for the system is definitely applicable, especially by adding more cameras along the two axes. So that will give us more baselines, more depth from different baselines, and that adding more information to the system will definitely give us better result and quality. So this system, we designed it is just to figure out would it work better by looking at the scene with more cameras. So basically this this research is trying to find out if it's applicable to add more camera to help improving the quality. So basically, I think it's already proved by the research. And for sure, in the future, why don't we just add more cameras and figure out if there's better quality we can get? And also for the camera, better quality camera, we have like now our cameras are in 2K, and because due to COVID, I have to work on my projects at home. So I only have very limited processing computer for the cameras. But as we can go back to the university and work on higher resolution cameras, and our computer will be able to handle more data, then we definitely will get better resolution and quality of the depths.
All right. How can this technology be applied to the marketplace?
The marketplace, like in the visual effects industry? So like we explained in the presentation, so when we are filming, like just take an example from the Tom Cruise Mission Impossible. He was running into the sandstorm, but for creating a better, more realistic effects that he's actually in the sandstorm, they have to man-made some like sandstorm and ask him to run into it, because current technology wouldn't allow us to reflect the depth gradient of an object or a character. But with our system, we are able to get a depth and also accurate depth for a live action character or an object, so that we can composite such effects into the scene vividly, realistically. And we don't have to ask this like characters run into such like storm, sandstorm, like fire and explosion. So yeah, I think that's somewhere we can apply it. And also, if it goes to certain accuracy, then we don't need green screen anymore. That would be another like huge jump in visual effects industry.
Great. Well, thank you, Leah. Oh, we just had one more question come in. Have you investigated the use of inexpensive cameras surrounding a central high resolution camera as a cheaper way of building depth data?
So we haven't explored of using, but the cameras we are using now is not very expensive, to be honest, because the research is aiming to work for film or say visual effects industry. So we're looking at high quality. So I think matching the camera's resolution with the surrounding camera would be very important. But if we can get some assistance from like machine learning, deep learning, then, well, it's probably not going to be a problem anymore.
Great. Well, thank you so much, Leah. Very great conversation and for sharing your research.
Thank you. It's great to be here.
Yeah. I also just wanted to thank everyone for taking the time to join us today, and hope that you really did enjoy the conversation as well and gain some valuable insight and information. So just a reminder that today's event will be posted to Carleton's YouTube channel. So I'm just going to share a survey on the screen. And if you do have the time to fill it out right now, we would much appreciate it. All answers are anonymous. And just wanted to say, as we wrap up Ingenious Talks online for 2020, we really want to thank you for your support in these events as we've transitioned to the online world. So looking forward to 2021, we can't wait to bring you more innovative research and information talks. So on the screen, you can see various ways that you can stay connected with us, and that our next Ingenious Talks Online will be hosted on January the 20th. Right? Stay safe and happy holidays. And thank you again, Leah.
Thank you.
Take
Happy
care.
holiday, everyone.